Okay, so we start a new lecture again, lecture 6. So we will just first do a bit of recap of what we saw earlier. So in the previous lecture we basically started with the mixing of two components A and B, because in practical systems we are dealing with impure systems which consist of more than two or more elements. So we start with binary solutions consisting of two elements. So we looked at the free energy delta G that happens by mixing two elements, and this was basically delta H mix minus delta T delta S mix. So for G2 to be lower than G1, which means the free energy, if solution is stable, then G2 has to be lower than G1, and this delta G term, which is the free energy change upon mixing, that is free energy of mixing, is nothing but delta H mix minus T delta S mix. So delta H mix is the change in the enthalpy or the heat content of the system, and delta S mix is the change in the entropy of the system before and after mixing. And we first started with regular solution, which means that for regular solution we assume that delta H mix is equal to 0, which means there is no change in the enthalpy after mixing, and it remains the same, which means delta H is 0, but there is a change in configurational entropy. There is a change in entropy which we were working out. We are also then we moved on to entropy, and we said that entropy is thermal and configurational, and we have chosen to ignore the thermal contribution to entropy because of if there is no substantial, if there is very negligible change in the heat in the temperature or volume of the system, then we can say S thermal is negligible, especially in the solid state, and we only work with the configurational entropy. So now let us see how do we evaluate the configurational entropy. So we say all right. So we said that we will ignore thermal entropy. So S is equal to S config. So before mixing, so we had pure A and pure B, and for both of these S1, so S1 was equal to 0, because whether you had pure A and pure B, the number of ways in which, because it is equal to K ln W, okay, and W is 1 as long as it is pure A and pure B. As a result it is KB ln 1, and this will be equal to 0. So for both these states the entropy was equal to 0. So as a result, if you take their weighted sum, then that will also be equal to 0. So S1 is equal to 0. Okay. What about S2, which is after mixing? So after, now we look at after S2 is equal to KB ln W2. Okay. So what is W2? W2, now what is the lattice like? You have now let me draw the lattice here. You had a situation like this. Now some of these are, so you can see this is A, this is B. So A is in proportion XA, B is in proportion XB, but as long as it is a random solid solution, which means position of A and B cannot be fixed, the A and B can be randomly distributed. If they can be randomly distributed, there are multiple ways you can arrange A and B, and each manner can be different. So this is one possible manner. In another possible manner, you can have situation like this. So, just count the number of atoms. I have marked 5 atoms as gray. This is another configuration. So, you can have configurations. Now, this is only about 16 atoms that I have taken, but a system has much more larger number of atoms. If you take 1 mole, it will have 6 into 10 about 23 atoms. So, which means you have numerous ways of making distinct configurations of atoms by mixing A and B. So, if that is the case, then W can be defined as factorial of Na plus Nb, number of A atoms, and this is divided by factorial of A, Na and factorial of Nb. So, this gives me the total number of possible distinct configurations in which I can arrange should be Nb. I can arrange A and B in a solid solution of AB distinctly. So, this Na is the number of A atoms, and B is the number of B atoms, and Na plus Nb will be equal to N, which is total number of atoms. So, Na divided by N will be Xa, and Nb divided by N will be equal to Xb. Okay. And if you take for 1 mole of solution, if I take 1 mole of AB, then Na can be equal to Xa Na, and where Na is nothing but Avogadro's number, which will mean 6.023 into 10 to the power 23 atoms per mole, and Nb will be equal to Xb into Na, again same thing. Okay. So, we are just going to take for 1 mole because free energy is a molar quantity, and that will be simpler later on, as we will see. So, now to solve this expression, we have seen that W2 is equal to Na plus Nb factorial divided by Na factorial into Nb factorial, and we know that S2 is equal to Kb ln W2, which means S2 will be equal to Kb into ln of Na plus Nb factorial minus divided by Na factorial into Nb factorial. To solve this, we need an approximation which is called as Stirling's approximations. Which says that ln x factorial is equal to ln x minus ln x ln x minus x, not ln x. Okay. And another thing that you may, and we can also define gas constant as R to be equal to product of Na into Kb, which is product of Avogadro's number, and Boltzmann constant is R, which is gas constant. So, now when you do that, now S2 is equal to Kb ln of Na plus Nb factorial minus ln of Na factorial minus ln of Nb factorial. So, this will be Kb. So, you can see that this will be Na plus Nb into ln B minus of Now, let us look at the second term, minus of Na ln Na minus Na, and then minus of Nb ln Nb minus of Nb. And if you solve it, you will get S2 to be equal to minus of R. In fact, what you will get is basically, so you replace, so in the above expression replace Na as Xa Na, Nb as Xb n small a, Avogadro's number, and what you will get is basically S2 as minus of R, or in fact I will write Kb Na into Xa ln Xa plus Xb ln Xb, and this I know is R. So, this will be minus of R Xa ln Xa plus Xb. As a result, delta S mixing will be nothing but S2 minus S1, and S1 was equal to 0, and this will be minus of R Xa ln Xa plus Xb ln Xb. So, this is the free energy of mixing that you get after applying, after working out the expression for configurational entropy, assuming that thermal entropy change is equal to 0. So, you can see here, since Xa and Xb are less than 1, delta S mixing is greater than 0. So, you can see in the above expression, since Xa is smaller than 1, Xb is smaller than 1, log of these are going to be negatives. As a result, negative will become positive, and as a result delta S mixing will be greater than 0. So, which means that entropy increases after mixing. So, mixing results in increased entropy. Okay. So, we can write now the expression for delta G mixing for a regular solution, because delta H mixing was, so for a regular not for a regular solution, I am sorry, for an ideal solution, of A and B, for an ideal solution of A and B, delta G mixing is equal to minus T of delta S mixing, which is equal to R T Xa ln Xa plus Xb ln Xb. This is delta G mixing. So, now if you plot it, you can also plot it. So, you can see from the above expression that since Xa and Xb are smaller than 1, lower than 1, delta G mixing is going to be negative. So, as a result, I am going to plot this below 0. So, this is 0, this is pure A, this is pure B, and this is change in Xb. Okay. So, if you plot delta G mixing as a function of Xa and Xb, so if I put delta G for, so you can see that delta G mixing for Xa to be equal to 1 is 0, and it is also 0 for Xb equal to 1. So, actually it is not actually exactly going to touch the, so it is not going to exactly be equal to 0, it will be actually asymptotic, but nevertheless because if you take the gradient will not be equal to 0. So, basically for a schematic it will be something like that. So, this is at a fixed temperature T1. If you increase the temperature T2, it will go to, because this is T2. So, T2 greater than T1 leads to higher. So, you can see that this depth has increased as the temperature increases. So, you can see that delta G of free energy of mixing becomes more and more negative at higher temperatures. So, that explains why things mix better at higher temperatures than at lower temperatures. Of course, there are kinetic arguments as well, but thermodynamically the free energy of mixing is more negative at higher temperatures than at lower temperatures, and mixing is preferred at higher temperatures as compared to lower temperatures. So, let us now move on to so basically this free energy of mixing, delta G mixing, you can say is the driving force for mixing. Okay, and this is very obvious. I mean, when you try to mix for example very simple things like sugar and water or salt and water, they mix far more easily at high temperature than at low temperature. Of course, there are solid solubility arguments as well. But let us say we are in the solubility limit, even then and kinetic arguments, leaving aside the kinetic arguments, the mixing has higher driving force at higher temperatures than at lower driving force, and that is why you see them in practice as well. So, the actual free energy now we said that G2 was equal to G1 plus delta G mix, and this G1 was XAGA plus XB GB, and this has an additional term now RT XALN XBLN XB. So, this is the overall free energy of the solution, and you have to appreciate that this term actually is negative, and that is what makes the free energy of mixed solution lower than the pure solution. So, if I now plot it, so so this is molar free energy G. Okay. So, if I plot for example at a given temperature, the free energy follows this kind of behavior. This is GA, this is GB, and if I, so let us say this is at temperature T1, if I do the same now at temperature T2, which is higher, now free energy of course has decreased. So, this is at T1, this is at T1, this is at T2, this is at T2, and this will be now the free energy of. So, you can see that this is the delta G mix T1, this is delta G mix T2, which is higher. So, delta G mix at T2 is, so higher means it is more negative. So, it is so T2 is greater than T1. So, one thing with that you have to note is that the intercepts on the y axis, they are not exactly intercepts. The curves, the free energy curves actually go tangential to the y axis at xa and xb, and that you can verify by, so if you look at the free energy expression, take the derivative of G2 with respect to XA and XB, you will see that it will not be, it has to be asymptotic, which means the curve goes on x and y axis as if it touches. So, if you zoom it, what you should obtain is basically, if I just zoom it, let us say this is XA and the curve will go like this. Something like that, okay. So, it does not actually intercept, it just goes parallel to, so this is G. So, here it is, you can say asymptotic, and for this you can just take del G2 by del XA or del G2 by del XB, and you can see the gradient will be infinity. So, it is not exactly cutting the y axis. So, now let me summarize this particular point once again. So, we started with, let's go, this is a very complex, this is an interesting thing to understand. So, we started with calculation of configurational entropy. So, configurational entropy is basically about a number of ways in which you can arrange the atoms within a lattice. So, before mixing it is pure A and pure B. So, there is only one way of identifying the or mix, there is only one configuration in which you can see the atoms. As a result, S1 is equal to 0 for both A and B. As a result, the net entropy before mixing is equal to 0. After mixing, however, you can have different configurations if A and B are randomly distributed in the lattice, and as a result, if you have Na number of A atoms and Nb number of B atoms, then the W2, the parameter of randomness, is nothing but factorial of Na plus Nb divided by factorial of Na into factorial of Nb, where Na and Nb are nothing but if you have 1 mole of solid solution, then Xa Na and Xb n small a, which is Avogadro's number. So, W2 can be further modified using Stirling's approximation, and what we will get is entropy, which is, so if you do analyze it, we get S2 as minus of R Xa ln Xa and plus Xb ln Xb, and as a result the delta S of mixing will be S2 minus S1, which is minus of R Xa ln Xa plus Xb ln Xb. So, you can see that here since Xa and Xb are smaller than 1, the entropy change is always positive. So, when you are going from pure A and pure B to AB state, the entropy change actually is positive. So, basically we are saying that mixing results in a positive increased entropy. So, for an ideal solution of A and B, delta G mixing is minus T of delta S mix, which is RT Xa ln Xa plus Xb ln Xb. And when you plot this delta G mixing as a function of temperature, what we see is that for pure A and pure B, of course there is no mixing, so it is equal to 0, but for any intermediate composition range, there is a decrease in free energy of mixing, which means there is a negative free energy of mixing, which results in, which is what makes mixing possible. If it was not negative, you would not have mixing happening, and as you increase the temperature, the delta G mixing also decreases further, which means the driving force for making a solution increases as you increase the temperature, and this is what is important to understand. So, delta G mix is nothing but driving force behind mixing, and G2 is basically nothing but G1 plus delta G mix. So, the final free energy after mixing G2 is XAGA plus XVGB. This is the original component before mixing, and what you have added, the third term is RT ln Xa plus into ln Xa plus Xb ln Xb, and this term is negative, and so this is what is true for most systems which make a stable solid solution, that when you mix them together it results in a free energy where delta G of mixing is negative. And if you plot now the overall free energy, the molar free energy shows this kind of trend. So, you can see that you were somewhere here and now you have gone somewhere here. So, this is what is the driving force. So, if I draw in a separate plot, this is delta, this is GA, this is GB, and if I just take the weighted average, sorry, this is GB, okay. So, if I take a composition XB, this is what is the weighted average. Now, weighted average basically says that I am at a free energy which is higher than that of A, okay. Now, it does not, so you can't really mix. The mixing is made possible only because you had a decrease in the free energy from this state to that state, and this is delta G mix, and this is basically negative, and that is what makes the mixing possible, because now you are in a free energy state which is lower than the free energy of the mixture. As a result, you have a stable solid solution. So, this will make stable solid solution. We will see later on now. So, what we will do next is, not today, but in the next few classes we will, next few lectures we will look at the concepts such as chemical potential, which is necessary to understand the effect of compositional changes in the regular solutions, because what we have talked about until now is the ideal solution, and now we will look at the chemical potential, we will look at the regular solutions. In the regular solutions we will study chemical potential, we will study the effect of deviations from ideality. And that will make us understand what happens in reality. In reality, whether what makes a solution stable or unstable, because not everything is mixable. So, not everything makes a stable solid solution. So, we will see that in next lecture as to what do we mean by what are the practical implications of deviations from ideality. So, we will do that in the next class. Thank you.